Hey, good morning. Let's start. I know I'm not very sure if others are going to join, so let's start. Why to waste time, right? So today, I'll not be going over the revision of what we have done in the last week. Uh, I believe there were some assignments that you had to do on the LDOs. Probably you have done it. If not, it's up to you to do it. I'm going to take different topics, as I mentioned last week. So there are two topics in front of us. One is the voltage and current references. Second one being the PSRR. So we will cover these two topics in today's and tomorrow's class. First, let me pick up PSRR because it's also closely associated with the LDOs. So if we understand PSRR, most probably we have completed almost, I would say, a lot of aspects of LDOs. Probably we can stop there and then proceed to the next point. That's the voltage and current references. Meanwhile, let me start today's topic. That's PSRR. To begin with, let me share the whiteboard and then we can discuss further. Okay, so what is PSRR? Power supply rejection ratio. If you look at the PPT that is shared by Takshila, you have line regulation, load regulation, then also there are other specifications as well as ICMR, CMRR, so on, so on, so. But these two form a very important things. What is line regulation and what is load regulation? So load regulation is something when load changes, how much of V out changes. Because this LDO is in regulation, we want to make sure that this load regulation is very good, meaning we shouldn't have anything, we shouldn't have any fluctuation at the output because of the load, which typically doesn't happen. But yeah, uh, this is what it means. What happens when the load changes? How good does your loop regulate? That's load regulation. What about line regulation? Line regulation is regarding the supply. If supply changes, how much of V out changes? How much of change do we see on V out? Meaning, let's say you have a good LDO. I'll just represent it as a block diagram. And you have to regulate it to 1.5 volts. I'm just giving an example with the VREF of 1.2 volt. This is a supply, which will, let's say, vary all the way from 2 to 3 volt. It has that kind of a range that it can swing from 2 to 3 volt. It can change between 2 to 3 volt. So 2 to 3 is a huge range. Why? Because at 2, you have only a drop of 500 millivolts. At 3, it becomes 1.5 volts itself. So it's a huge number, right? So there is a possibility that whenever this kind of a change happens in the supply, the LDO loop internally, all the transistors are supposed to be in saturation. Keep that in mind. There's a good possibility that one or two transistors may go out of the saturation because of supply variations itself. At 2 volt, maybe everything is in saturation. At 3 volt, some of the devices internally may go out of saturation to, say, linear region. Cannot be avoided, right? Yeah, of course. Our job is to make sure that all the transistors are in saturation across the supply range. That's different thing. But there is a possibility that you have already built an LDO, but somebody who is verifying it gives a supply beyond what you have designed for. You might have designed for 2 to 2.5, thinking that our supply will vary only between 2 to 2.5. But verification guy, he is given an additional target to verify even at 3 volt. In that case, some of the transistors may go out of saturation, because of which there could be accuracy loss. 1.5 may become 1.49, or it may become 1.6. Don't know. It depends on how bad the transistors go out of saturation, or how bad the loop is no more working. So depending on that, you will see a huge variation when the supply is changing. Okay, so this we should see, and that is called line regulation. Now, what is PSRR? Is PSRR and line regulation same? See, PSRR is, again, it has power supply as the word. PSRR means, see, line regulation is more of, let's say you're regulating at 1.5. So this is a supply. Let's say X-axis is a supply. So from 2 to 2.3 it was okay. From 2.3 it started to deviate and it started to go up. It was 1.5 here, it became 1.6 here. Okay, meaning it's just varying the supply in DC terms. Meaning the line regulation is more of a DC parameter, or I can also call it a large signal parameter. Large signal specification, let's put it that way. Coming to PSRR, it is also very similar, that it also looks at how much of the change we see in the output. However, the change is different here, meaning, let's say PSRR is a AC or small signal specification. Meaning, if there is a AC component that is present in the supply, why would there be AC component? The supply typically goes to a lot of places. It may be an LDO, it could be going to an oscillator, it could be going to highly switching circuits, it could be going to some PLL, it could be going to ADCs. A lot of places the supply goes. When it goes to a lot of places, all those noise, all those current consumptions from various blocks are affecting your voltage node here. See, anytime, just keep that in mind, that any voltage source will have a resistor, right? Now, this is the point you tap for your LDO. There could be some more where you tap it to oscillator. Some more point where you tap to some other loads. So 5-6 loads are there. There'll be 5-6 tap points. Now, what is the issue here is that, let's say your oscillator takes the current in bursts, more like this type of current. Whenever oscillator switches, there will be huge current. So if this huge current has to travel through this resistor and through this resistor, what does it mean? The voltage which was here, let's say 1.5 volts, it could be an LDO, or let's say 2 to 3, right? Okay, let's say this is a battery where it is supposed to be 2 to 3 volts, so anywhere in between. Let's say it is at the minimum 2 volt. What happens if there is a huge current taken in this path? This path, we'll see it was 2. When the moment there is a current being taken from the oscillator, this drops. There'll be a drop. It could go up to 1.9, 1.8, whatever it is. But there is some component and there is drop, which you could associate with a particular frequency. You can see that there is a fixed time interval here, just because of the oscillator I'm talking about. It's a fixed interval, meaning anytime there is a periodic and repetitive pattern in current or voltage, you can always associate it to some frequency components. If oscillator is working at, let's say, 1 gigahertz frequency, your current consumptions may be typically, this is every half cycle there will be current, at least. Let's say every half cycle, meaning every 0.5 nanosecond there will be current being taken in something like this. So this is a voltage, the battery voltage, right? The battery voltage will have spikes every 0.5 nanoseconds, meaning you have a 2 gigahertz noise on your battery or 2 gigahertz noise on your supply. Now, why are we really analyzing this, right? Ideally, our supply must be clean, ideally. But it doesn't happen in real life scenario. We will see some noise on the supply. And as the supply is from which we are deriving the output voltage of 1.5 for the LDO, there will obviously be some coupling. When I say coupling, a part of the supply will also appear at the output of the LDO. Now, is it desired? No, it is not. We want to make sure that irrespective of the supply, our LDO output is always clean and we always get 1.5. It has to be a constant voltage throughout. The supply varies. Supply has a frequency component, because of which the LDO may also have a very similar frequency component appearing here. As I mentioned earlier, it is not desired. We do not want to have it. Now, how much of it, our circuit, there are circuit techniques where you can remove, you can reject the power supply noise effectively. How much of noise we can reject, how much of power supply related noise we can reject. That is what is PSRR, power supply rejection ratio. Okay, any questions here? We'll look at the details. Probably there is a very nice curve, which is a very common interview question as well, about how the PSRR looks like, how the PSRR plot looks like. We'll go through it. But till now, I believe there shouldn't be an issue. This is all the basics of PSRR. Right? Okay, let's go ahead and jump into the analysis part of the PSRR. Give a minute. Let me share the material that I had prepared some time back. I hope you are able to see this. Okay, this is from my previous, for the previous batch I had done this material some time back. We'll reuse it. Now you are able to identify what this circuit is clearly. Let me annotate. Yeah, you are able to anyways look at this circuit and clearly say that this is an LDO. R1, R2, clearly it's an LDO. But what about RESR and CL here? These are the load capacitance. Every capacitance is also associated with the equivalent series resistance. That's called RESR. Okay. So RESR is always a part. We cannot leave it. For the time being, you can also assume it to be a 0-1. But let's have it for the sake of understanding if there is really a ESR, how does it matter. Okay. Now what I have done is, we would like to make sure that our Vout is free from any noise at VDD. Any noise at the supply, it should be free. So there shouldn't be any noise coming on to Vout node. We also know that the driver will always be in saturation. Now, keeping that in mind, we can have the output circuit only, this part of it, represented by something like this, where RDS is the resistance of the MOSFET, the MOSFET driver. There will be a Z0. Z0 stands for the output resistance, which you can easily guess. It is the impedance offered by the CL plus RESR in parallel with R1 plus R2. So these two networks coming in parallel, that will be our Z0. Okay. There is also another resistance. Don't assume that these two are coming in parallel. So Z0 and Z0 reg. We'll look at that, what comes and what is not. Z0 reg is the resistance of the regulator, which when it is working, what happens when the regulator is working? The output impedance reduces by AOL beta factor. It reduces by AOL beta factor. Okay. Now, if the output impedance reduces by AOL beta factor, but what is it? When it reduces, there should be a, what reduces, right? What reduces is, when you look at the impedance from here, it is the impedance looking downwards, which is Z0, which we earlier calculated, parallel with RDS. Z0 parallel with RDS, whole divided by AOL beta when it is getting regulated only. Okay. Now let's go to the next slide and try to analyze what's happening here. Give a minute, I'll see if I can make it full screen. Probably not. Okay. Okay, something is better. Okay. Now there are multiple ranges of frequencies that we will talk here, because we are talking about the frequency component in the supply. It's a AC analysis, or it's a small signal analysis, where we start talking about the higher frequencies. Or in terms of frequencies, it's not just the DC that we're talking about now. It is a frequency related component. Now at low frequencies, what happens? At low frequencies, you are sure that your LDO is operating, LDO is working, the regulation loop is in place, right? If the regulation loop is in place, we will only consider Z0 reg. Okay. If the regulation loop is broken, then only we will go and consider Z0. Z0 reg, because it is, the loop is being regulated, and hence it is Z0 reg. Okay. Now at low frequency, what happens? We already know that Z0 reg is Z0 parallel RDS divided by AOL beta. What is V? Now you can consider this as a simple resistor divider, right? So your V out by VDD is nothing but a simple resistor divider. What component of VDD appears at V out? It is Z0 reg divided by RDS plus Z0 reg. It's a simple resistor divider. Now you go and substitute Z0 reg. Z0 reg is what? Z0 reg is ZO RDS divided by AOL beta. Yeah, taken in everything. Then I assume that ZO parallel RDS. ZO is, I may assume that, some of the assumptions that I take, and then I assume that ZO reg parallel RDS is equivalent to RDS. It's just an assumption here, and you will reach a point where it is 1 by 1 plus AOL beta. All the other terms we cancel. Finally, what remains is 1 by AOL beta, meaning you have a loop gain. AOL beta is nothing but loop gain, right? At low frequencies, the gain, or I wouldn't call it the gain, but how much of VDD's noise will appear at Vout, that will be 1 by AOL beta. Meaning, if your DC gain in your STB simulation, you get a DC gain of 60 dB. Okay, your Vout by VDD, or the power supply rejection ratio, will be 1 by 60 dB, which is minus 60 dB. 1 by something in the dB scale will become minus 60 dB. So you have a very good rejection ratio. So when you 1 by 60 dB is, minus 60 dB will become, I'll give you that, let's say, minus 60 dB is 10 to the power minus 3. The gain is 10 to the power minus 3, meaning if you apply 1 volt at VDD, what you're going to see at Vout is 1 millivolt. 1 volt of AC, 1 volt of sinusoidal, 1 volt peak to peak sinusoidal signal you apply at VDD, what you're going to see is only 1 millivolt at Vout, which is a very good, I would say it's a very good number. For PSR. So, meaning you have a AOL beta. If you look at the DC gain of your overall LDO, it looks like this. This is the AOL beta that we are talking about. Then there comes a pole, right? Now, what you saw here, Vout by VDD is 1 by AOL beta. Meaning, anything you see in this curve gets inverted in the PSR curve, at least in the low frequency domain. Okay. Then what does that mean is that if there is a pole at pole location P1, I don't know, it should be an input pole because it's a PMOS driver. Whatever the pole we have at P1, that pole in the actual gain becomes 0 in PSR. This is PSR, this is gain. If there is a pole in the gain plot, that becomes a 0 in PSR plot. Okay, so the curve, how does it look like? If, let me choose a different color just for the discussion. If pole is here, the PSR plot was something like this, which was minus AOL beta, right? At this point, it starts to rise because the 0 here will give you 20 plus 20 dB per decade. It starts to rise. Okay, meaning you had a very good power supply rejection in DC till pole P1, or now it becomes 0 in the PSR plot. But anyways, till P1, the rejection was very good. Now the rejection slowly worsens, meaning the curve is moving up, meaning the VDDs, any noise at the VDD is starting to appear slowly with a higher quantity at the node V out. The gain is slowly increasing. But till where? There should be a limit, right? So there was always a UGB for the, this curve had a UGB and it could have gone down depending on the second or third pole. What happens with the PSRR plot is something different. We'll go there next. PSRR plot is something different, but at low frequencies, it does follow the inverse of the DC gain plot. Now, let's see. Let me erase. Let me capture this image, erase everything. Go to the next slide. Now, we had the expression V out by VDD is equal to RDS by RDS plus AOL beta RDS. This is coming from the previous slide. We had this. But AOL itself has a pole, right? So if you have to represent AOL in terms of, also with respect to the frequency components that is present, or in other words, if I have to also add up the poles and zeros, give me 1 minute. Okay, if I have to also add up the poles and zeros, the expression becomes AOL, which was simple AOL earlier, it became AOL by 1 plus S omega 1. Omega 1 is a pole in the DC gain curve, and now it is a 0 in the PSR curve. Okay, now what I am trying to do here is, let's simplify it. When you simplify it, what you get is, you look at the expression. I just simplified it. It is not something huge. I have not made a big assumption anywhere. So it becomes 1 plus CS by omega in the numerator, meaning in the numerator we have a 0. That's what I already mentioned, right? There should be a 0 at omega 1. At low frequencies, we have a 0 at omega 1 in the PSR plot. That's what we theoretically or equation wise we calculated. That's also visible here. Now you further simplify it, what you get is AOL beta omega 1 as the location of a 0 for the PSR plot. Sorry, location of a pole for the 0 plot. Whatever is in the numerator is 0, whatever is in the denominator is a pole, right? So 0 is clear that at omega 1 we had a 0. Now, what about the pole? You see that the expression says AOL beta omega 1. What does that mean? AOL beta omega 1. This is your gain. This is your 3 dB bandwidth. Gain bandwidth product. What is gain bandwidth product? Gain bandwidth product is nothing but unity gain bandwidth. So this expression gives you unity gain bandwidth of loop. Meaning, at the unity gain bandwidth of the loop, you have a pole in the PSR plot. Okay, how does it look like? Now I'll use the same color for your convenience. It was like this PSR plot started to move up. This is omega 1. It moves up to some extent, and at PSR, sorry, at the UGB, there will be a 0, meaning the curve flattens out. Okay, it's only till the UGB we see this, and at UGB it flattens out because of the pole that we have at the UGB. Okay. Okay, coming back. The next, so we have analyzed couple of frequency ranges now. So 0 to first pole to UGB is analyzed, right? So we understood that there is a Z in the PSR curve, there is a 0 at omega 1. Here, there is a pole at UGB. This understood? This is understood. Now, post UGB, what happens is the question. Post UGB, now the gain, overall loop gain is less than 1. If it is less than 1, what's going to happen is that your ZO reg doesn't really hold good because the loop is not really working. The loop gain is less than 1. So meaning your overall output stage gets simplified. You may ask, okay, why is then RDS, right? Why shouldn't it be something else if the loop is not working? I told the loop is not working, but it doesn't mean that the output driver is not working. Output driver may still be in saturation. Hence, we will still consider RDS as the driver's resistance. And we have the network of the resistances R1, R2, RESR, and Cout in place. We are not going to consider ZO reg now, just because after UGB, it doesn't really make sense to take it into account. Loop is not working, right? Okay. Now, if you analyze the circuit here, what is a pole at the output? The pole here. There'll be a pole at the output. There is also this output pole coming into picture. That output pole is given by ZO plus RESR into Cout. Okay. Now, that is this output pole. Because there is a second pole, it starts to reduce again. The curve reduces, meaning your power supply rejection starts to get better because of this pole, the output pole we call. Okay, you can calculate what the pole that is coming at the output. It is most probably we can simplify it to this expression. I had a detailed calculation somewhere. Let me share it as well. There is a good paper on this. I will also share that over the group, maybe today after the class. Okay, so now because of this pole, that's the output pole, the curve again starts to fall. Okay, why does it fall? Because the PSR is now nothing but ZO divided by ZO plus RDS. This overall expression starts to decrease over frequency. Why? Why is it decreasing over frequency? You may see that you already have a ZO, right? What is ZO that we calculated earlier? ZO was parallel combination of R1 plus R2 parallel with RESR plus ZCL, or the impedance because of the Cout. Now this Cout is the effect of impedance. starts to decrease because of Cout. The capacitance impedance decreases over frequency. At high frequency, it acts like a short. So you have a Z0, which is decreasing over frequency. This also decreases over frequency, but overall, RDS is still more or less a constant value, because of which you may see that overall expression Z0 by Z0 plus RDS, it is going to decrease over frequency. And that decrease results in this range. After UGB, after the second, the output pole. Now, does it fall continuously? It may, if there is no RESR. If there is a RESR, at some point of time when the Cout effect becomes a zero resistance, Cout gets shorted at high impedance, high frequency, right? So if at all Cout becomes zero, then effectively the circuit you have will be this RDS, R1, R2, and RESR. The cap is now shorted. Typically, RESR could be a very small value when compared to the R1 and R2. So R1 and R2 you can ignore. So what remains is RDS and RESR. Meaning at very high frequency, the PSR is RESR divided by RESR plus RDS. It's a constant number. There is no frequency related component. There is no capacitance here. There is nothing that's changing over the frequency. Of course, assumption is that our output driver is still in saturation, right? So in such case, if there is an RESR, it just stays at this point, this line, because at a particular frequency, when Cout becomes a zero impedance, only RESR visible, and RESR divided by RESR plus RDS will be the equivalent PSR, power supply rejection. It will continue to stay in this line. Now, what is this? This is a zero. If you look at the curve's shape, because of the slopes and all, this clearly is a zero. And that zero comes because of RESR and Cout. These two combinations make probably the zero there will be more or less the RESR. This will be the frequency of zero. 1 by RESR Cout. Okay. So overall, if you look at, let me see if I have more slides here. This is something different. Okay. Okay. Overall, I'm going back just after saving this image, going back to the whiteboard. So if your gain plot looks like this, okay, so maybe somewhere here is your UGB. Okay, if your gain plot looks like this, your PSR plot is going to look like this. It's a negative gain. The first pole is exactly the same. Now it starts to move up with plus 20 dB per decade. Ideally, it has to touch around UGB only. There's this, whatever I told, right? Around UGB. Then it starts to flatten out. Because of the output pole, it starts to fall. Something like this. If I have to smoothen it out, it looks more like this. This is the PSR plot, which is very, very common across, almost all the interviews. This PSR related questions will be there, especially when you're, let's say, 2 or 3 years experienced. You have to understand what are the different regions, which is till here one, till here one, till here one, then onwards one more. When will be the worst case PSR that we have? That is when the PSR is the highest. Okay. The PSR becomes the highest when near the UGB. It's always near the UGB. There will be a worst case PSR that you'll be seeing. Now, is there any way that we can reduce the effect of the supply noise on the output? Is it just that we have just calculated from whatever we have, whatever the circuit we have, we calculated the PSR plot now. But the question is there any way where we can reduce the PSR, the power supply effect at the output? Can we make our power supply rejection better? Is it possible that we move this curve down or this down, or achieve something like a plot more like this? It shouldn't even go near the UGB. Is there a way to achieve this so that power supply rejection is always very, very good? No noise at the power supply will affect our output. Is there any way to do that? That is the question I have. Let's think about it. We do have some ways. What are those ways? What do you mean? What do you think is that way? I hope you're able to see my screen, but I see a Takshila VLSA at the bottom. Not sure why. Okay. Now we understood the overall concept of PSR, that how does the curve look like? How much of a rejection will we have? When are we going to have the maximum power supply noise coming into the output? That's around UGB. Now let's try to identify the ways on, see, the analysis that I did in today's class is coming from a paper, and it has its flaws. It doesn't mean that whatever I have mentioned is always true or it is the ultimate. No, there are other ways of analyzing. There are other ways of getting the things to have a better PSR. Let's just look at some intuitive ways of how can we avoid the power supply noise coming to the output. Let's consider a NMOS driver. And I'll just consider one resistor here. I don't know what the output is. Let's say V out. I want no noise of V sub to come to the V out. Ideally, what is V out? I'll just put it as Vx. What is V out? Ideal case, V out is Vx minus Vth of the transistor. Right? Now, what if The VTH is not changing with respect to the power supply noise. It is always constant. Yes, that's true. Is there a VT changing in this NMOS because of, let's say, the body bias? May not be. Because ground, we have not considered any ground noise. It is only the supply noise that we considered. So when we consider only the supply noise, the VTH more or less will remain constant irrespective of what power supply noise we have. What about VX? Does VX have a noise? We don't know. VX is coming from another op-amp, right? So I really do not know if the op-amp has some noise. If the op-amp has some noise, what happens? The op-amp output has some noise. The VX will have some noise. And if it is correlated with respect to the VSUP, meaning VSUP itself is the reason for VX noise, let's say, it is possible. It depends on how good the op-amp we have designed. If Vx has a noise, that's going to straight away come at Vout. It's going to appear directly. Vx has a noise, it is visible on Vout straight away. Can we do something about it? Not much. If Vx has noise, Vout has noise. Let's say Vx does not have any noise. Vx is clean. No noise on Vx. What happens to Vout? Vout is also clean. So, meaning if Vx is clean, the output is clean. If Vx has noise, Vout also has noise. Let's look at the PMOS driver, which we tried to analyze a little while ago. Does the same theory hold good here? What if there is, I'll just represent VSUP also has noise, okay? VSUP has noise. What is output current? The output is nothing but IR, right? Output is nothing but IR. Here, in this case, what is I? Let me just do it as proportionality constant. What is VGS? VSUP minus Vx minus VTH whole square R. If VSUP has a noise, Vx is clean, VTH is clean, what happens? If Vx is clean, the current I is going to have some noise because of the VSUP. And hence, Vout will have some noise. If Vx has some noise which is correlated with VSUP, what happens? VSUP has noise, Vx has noise, they both cancel each other. I'm telling correlated noise between VSUP and Vx. They cancel each other. And hence, you get a cleaner I, and hence Vout will be a constant voltage. So for NMOS, the input to the gate has to be clean if the output has to be clean. For PMOS, the gate of the driver should have a noise, correlated noise, so that the output becomes clean. Of course, in the previous analysis, this kind of analysis was not done. We just looked from the impedance point of view. How does it look like? But here, what we are looking at is slightly from a different perspective on when the output is not going to have some noise. Of course, even if I say that it is correlated, let's say in the PMOS case, VSUP and VX should have correlated noise. The correlation will not be 100%. There will always be something different, slightly different. Whenever you have something slightly different, some of VSUP noise will creep into Vout. There is no doubt about it. Vout cannot be clean all the time. There will be some noise which will be creeping in from VSUP to Vout. It is going to happen. But how much? How much can we control is the question. Yeah. Probably let's take a break and come back. Let's take a break and come back by 9:10, and then we can continue from then onwards. Yeah, let's start. Yeah, I was discussing about when will we have, the better power supply rejection, especially considering the PMOS and NMOS drivers. What should be the noise at Vx, or the input to the driver? Should it be noiseless, or should it also have some noise? That's the question that we have currently. Let's start to analyze in a different way. How do we really get some noise at Vx? But clearly we mentioned that for this, the PMOS driver, we need some noise at Vx, which is correlated with the VSUP. So correlated noise is what we are looking at. We want to have some noise. How do we create some noise? How do we create some supply noise at Vx? Is there any way that we can create some noise, or is there any way we can insert some noise at Vx? What happens if, let's say, I'll put an extra circuit here between Vx and VSUP, which can couple the noise. What can couple the noise at high frequency? Coupling is just use a capacitance. Ideally, capacitance you connect between VSUP and Vx, it should couple the noise already. It should directly couple the noise across all the frequencies. Now, instead, what I'll do is I'll put a resistor and a capacitor and an RC. What will happen if I connect RC? Whenever there is RC like this between two nodes, one thing, of course, the low frequency will not be coupled. That's sure. High frequency will get coupled. From what frequency? There should be a frequency threshold from which then on there's a good coupling. That frequency is given by 1 by RC. This happens to be a zero location. The zero location is going to have, let's say, what was your curve looking like? It's looking like this, right? Now this RC adds a zero in the overall gain A beta. Hence, it adds a pole in your PSRR. So there will be a pole in the PSRR well before, it was going up to UGB earlier. Now, before UGB only, you can insert an RC, which will push or which will create a pole in the PSR plot, and hence it becomes much better PSR like this. Is not the earlier PSR where around UGB it was going very near to zero, meaning VSUP to Vout, it was almost coupling everything. Now, because of this introduction of RC, we have coupled a lot of VSUP noise onto Vx, which we wanted. Because this coupling has happened, Vx and VSUP noise are correlated, and hence Vout is now free of VSUP noise. Vout is working much better. At Vout, there is no noise seen is very, very less because of the VSUP. So PSRR becomes better and better. That's one of the side tricks that we use. is there any other way that we can say that Vx should have noise or shouldn't have noise for both NMOS and PMOS? What if we use a 5T OTA? Typically, we use a 5T OTA here, right? Just connect like this. Typically, we use a 5T OTA. This may be a feedback coming from here. This is VREF. This is PMOS, and feedback is positive, and this is negative. Now, looking at this, we use 5T OTA. Now, 5T OTA output is supposed to have a noise. We want noise at Vx. How much is the question? Anyways, we want to have a noise at Vx. Can we do something? Can we get something just from 5T OTA? How does the 5T OTA look typically? It's an NMOS input based. Something like this. Right. So you can see that from VSUP, there is one transistor that's here, which is in saturation. Note that it is in saturation. So even if you look at the impedance of this particular path right from VSUP, you say that the impedance looked from VSUP is huge. And impedance looked from here down is just maybe RDS. If you assume this to be a virtual ground, it should be only RDS N will be the impedance looking down. So overall impedance is what? Looking from the top is RDS N into 1 plus RDS P. What is it? It's what is the intrinsic gain? Intrinsic gain is GMP R naught P plus R naught P. So this will be the overall impedance that will be that you look at from VSUP. You look down, this will be the overall impedance. Looking at this node, it is RDSN. So there is some impedance that you can see like this. But it is not a very straightforward calculation that we have here. Intuitively going, you have, I can give you this simplified analysis may look like this. So you have two NMOSes down below. It's also an NMOS, right? Not ideal, hence not ideal current source. Hence, it's also an NMOS. So two NMOSes below, one PMOS. So what is near to the supply? Of course, the output point is near to the supply. Below to the ground, there are two transistors. Towards the supply, there is only one transistor. Hence, you may assume that there will be some contribution, some part of the VSUP that may be available at the output node of 5T OTA. Meaning, in other words, the 5T OTA is not clean. 5T OTA's output will have some contribution of the supply when compared to the contribution of the ground. Look at the ground, there are two transistors. Look at the VSUP, there is only one transistor. So it is more towards VSUP. So you may assume that there is some contribution of VSUP at the output. On the other hand, let's say if you plan to use a PMOS input based, how will it look like? The PMOS input based op-amp will look like this. Now, if it is a PMOS output based, what happens is from VSUP to Vout, there are two transistors. From Vout to ground, there is only one transistor, meaning the contribution of VSUP on Vout is lesser. So if VSUP has a noise, Vout transistor will not see a lot of noise. Vout transistor will see lesser noise when compared to the NMOS input based. Meaning, if you would like to have some noise at the VX node, if you want some noise, then go ahead and design an NMOS based input pair. If you want to have lesser noise at the VX, then go ahead with a PMOS based input pair. Meaning, if PMOS driver, NMOS input pair. If NMOS driver, it's better to have a PMOS input pair driver. Just looking at the PSR, nothing else. Okay, so but the combination goes like this. If it is a PMOS driver, go with the NMOS input pair. If it is a NMOS driver, then go with the PMOS input pair. That will give you better PSRRs. There can be exceptions. This is just a common guideline that people do follow sometimes, not all the time. If PSRR is one of the very important parameters for you in your design, then you may go ahead with this guideline. If PSRR is not an important guideline, then it doesn't really matter. Okay. Any questions here? If you look at Razavi also, I believe Razavi also has some good materials on this PSRR. Just take a look at it. If not, I'll also share the paper on the PSRR that we discussed earlier. It's a very good paper. You can take a look at. Okay. Okay. I believe PSRR is only that much. If we have, how do you simulate PSRR? Well, that's one question you may have. Let's just look at the simulation point of view. Then we will go to the next topic. Next topic, I may not be able to cover a lot today. I'll stop in between because it is a new topic. I'll start and then I'll give you introduction and then we will stop there. Okay. Let's see, how do you do the PSRR simulations? Are they difficult to do? What is PSRR simulation to be? You have done LSTB simulation or STB simulations where you just had an eye probe inserted in between. If you have done one, I have shown how to do it, right? So eye probe, I had inserted an eye probe between the feedback node and in the middle of the feedback node, and I had run a STB simulation. STB simulation is run only when we are doing the loop analysis, not if it is some open loop analysis of AC. We don't really consider STB analysis for that case. STB analysis is required only for the loop. So now, how do you calculate the PSR of any block? Let's say you have an LDO. I'm just putting it in the black box. LDO. You have the supply. You have an output Vout. You have the VREF. Ground. Now, you would like to look at the contribution of the supply noise or supply's AC component. It's a small signal analysis. Supply's AC component, you would like to see how much of it appears at the Vout. So in the setup, what we do is we put, let's say, 1.8 volt DC supply, and we give AC as 1 only for the supply. When we give AC 1 and run AC analysis, we don't do STB analysis, we do AC analysis. What happens is, initially it runs a DC simulation. It may not really show you that it has run a DC simulation, but it makes sure that it runs a DC simulation to set the operational points, operating points. Once the operating points are set, it will run a frequency simulation or AC simulation across the specified frequencies, where it will change, or only the AC will be applied at the supply. Then it sees, let's say if 1 volt is applied at 1 volt peak to peak is applied at supply, how much of it is really appearing at V out. So you plot V out in the results browser. You will see a curve more or less like this, which is the PSRR plot that we saw. So you have to run an AC by giving AC equal to 1 for the supply only. Okay, any question? Okay. Okay, then we'll go to the next topic. I believe if there are some doubts on this particular topic or in general LDOs, you must come back with the question and answers, questions at least, answers we can discuss. If you do not come up with your questions, probably I don't know what I'm missing. That's just because the more you ask the questions, the more clearer it gets. And also more I'll be able to explain. Otherwise, I may miss something out, and that may be a problem. Yeah. Anyways, let's go to the next topic. What's the next topic? Is the voltage and current references. Why are voltage and current references required? You have designed an LDO. In LDO, you took multiple current sources and voltage sources. I'm not talking about a supply, but there was a VREF used. Let's say that's 1.2 volt. There was also IREF used, or IREF or iBias, 5 micro, 10 micro, whatever it is. Where do you think these are coming from? What are these? Are these something that's already available? Are we going to input from the external world inside the chip? Or is it something generated inside the chip? If you look at the modern chips, modern day dies, they typically avoid giving anything from the external world. Although there are exceptions, but as long as possible, we make sure that everything is internal from inside the chip. So does that mean you have, let's say, a supply ranging from 2 to 3 volt, a battery supply, right? Can we generate a reference out of this? That's hugely varying. Let's say I have a resistor divider. Can I call this as Vref? No, let me call it as V out. Can I generate V 1.2 constant voltage out of this? No, will not be able to. Because V out will always be proportional to V sub. V sub varies, our output varies. Yeah, if I want 1.2 volts at all, it is not the right way to generate a reference voltage. What are the other ways? Is there any way where we can do it from using very simple circuits? No, even when you wanted to have an LDO, LDO is for what? For regulated voltage. You always wanted a reference there. You always wanted a reference. VREF. Now our aim is to generate VREF voltage and understand how do we really generate this. Before that, before going to the VREF, there's also IREF current that we were talking about. How do we generate IREF current? Which is difficult, whether it's IREF or VREF. Now, when you say constant current or constant voltage, what is it that we're talking about? I'm talking about the constant current irrespective of PVT, the process voltage and temperature. Probably we have already discussed about the PVT corners. What P is, what V is, what T is, and what kind of variations that we are talking about. You already know them. Irrespective of PVT corners, we would like to make sure that our voltage or current is a constant voltage and current. And now I'm going to go fast because I don't know, I'm not getting any feedback, man. Really, it's more like monologue. And I really do not know whether you're following or I don't know what is to be taught also. So, anyways. Taking a break. Let's come back after 10 minutes. I can't do this and do monologues for so long. Take 10 minutes break. I'll be back. Okay, let's start back. It will be simply a waste of time if I spend a lot of time like this. I'll continue with the topics. Okay, so our aim is to get PVT invariant current and voltage sources. PVT invariant meaning irrespective of what the process is, what the voltage is, what the temperature is. If I say that my reference current is 5 microamps, I have to always get 5 microamps of current. I cannot, if I say 5 microamps, I cannot get 6 microamps. It is not correct. So I have to always have that reference current intact. On the other hand, if something varies with respect to the PVT, let's say I told 5 microamps has to be 5 microamps. In such case, we call it IREF. But it can also happen that there are some circuits which are like in typical, they may give you 5 microamps of current. But according to the process variations or PVT variations, it may vary between a range, given range. Let's say it could be like 4 microamps to 6 microamps. Okay, it is a range across PVT corners, and it is okay to have such variations in the current also, and we probably our circuit is also optimized to take in these variations and then accordingly function. So in such case, we call this current source as I bias. So there is a variation, there is a small change, slight change between IREF and I bias. IREF doesn't change, bias changes. Very similarly, if you say 1.2 must always be 1.2, it will be a VREF. Let's say you also generate 1.2 as typical, but 1.1 to 1.3 across corners. In such case, we may call it as V bias. Okay. Both are very much useful. Both VREF and V bias are used very widely in all the circuits. However, there's always a need for a constant voltage and a constant current. So VREF and IREF, even if you consider any chip in the world, mostly you will have a VREF block, you will have a IREF block, or IREF and VREF generation will always be there. V bias and I bias could be some, it will always be there. V bias and I bias are very, very, very common. But VREF and IREF, it is more important to have them because using the constant voltage and constant current, we can do a lot of other stuff as well. So that's why we are also looking at PVT invariant current source and voltage source. To begin with, let's look at something known as a constant GM circuit, where we are going to generate a current which is supply invariant. Meaning, is it not process and temperature invariant? No, it is not. It is only supply invariant. With the process and temperature, the voltage does change, and it's okay to have it. So this is one of the circuit that is commonly used in almost all the dies. It's called constant GM circuit, or we call constant GM circuit, or we call it as beta multiplier. There are multiple names. It's basically, it generates a current bias, I bias, which could be used in multiple current mirrors and then used to get the required current bias as and when required. Now, what is this constant GM circuit that I'm talking about? Beta multiplier. I'll just draw a circuit. Probably during current mirror chapter, we have already looked at it, but let's say if at all I have a circuit like this. I don't know whether you remember whatever we have done earlier. This is R, and this probably is, yeah, K times W by L. This could be W by L. This could be W by L for P, W by L of P. Okay. So we have a circuit like this, very simple circuit. What is it doing? It's just mirroring the current, right? The mirror current which is flowing in the right side is mirrored to the left side. Whatever is flowing in the left side is mirrored to the right side. Basically, both sides there are one PMOS pair and one NMOS pair whose current is getting mirrored, because of which there is always a constant current. There are, in such circuits, typically there are two operating points. I could be 0 or I could be whatever you fix. Let me name it as I finite. Okay, this is what you designed for, but there could always be a 0 current, which also makes the entire circuit stable. Both legs have zero current flowing, and then because zero current flows in both the legs, nobody is really triggering the circuits. There is something that is triggering the circuit, because zero operating point is also a valid operating point. At some point, if you want to get some current out of this block, this circuit, there should always be a triggering circuit. That triggering circuit is what I'm talking about. Okay, now what is the triggering circuit? We'll see that later. But if you look at the circuit here, I'll just, for the time being, I'll just name it as I out. Okay, and this is I don't know, I1 maybe. Okay, now if I name the transistor as M2 and M1, VGS of 1, transistor 1 is equal to VGS of transistor 2 plus I out into R. Okay, now what is VGS1, VGS2? We can also represent in terms of the I itself. It becomes 2I out divided by mu Cox W by L equal to 2I out divided by mu Cox K times W by L plus I out into R. I simplify this, I can get I out is equal to I out. Note that both currents are I out only. It's a current mirror. Both currents are the same, just that I have changed the size of this transistor along with the resistor addition at the bottom and the source. So if I have to go and then simplify this I out expression, you will get something, a proportionality constant. Let me put it as proportionality constant C. Okay, maybe C dash divided by 1 by R square into 1 minus 1 by square root of K. Okay, this is your I out. I can get the expression for GM. GM is more or less it. GM stands as, there is an equation, right? 2I out mu n Cox W by L. GM of what? GM of this transistor. Let me name it as GM1. Okay, so this becomes, I'm just putting the equation from my previous reference, because derivation is going to take some time. It is going to be 2 by GM1 into 1 minus 1 by square root of K. The proportionality constant is more or less what we see in GM equation. C dash was what? C dash was 2 by mu n Cox W by L. Okay, so you have mu n Cox W by L here. And you can see that you can bring it out this side, I out by C, then you will get clearly the GM expression there. And for the resistance RS, I have gotten the equation, meaning the GM of the transistor, if it goes up here, is proportional to 1 by RS. The value of resistance that you have inserted and the ratio K, of course, there is a proportionality constant there. GM1 is proportional to 1 by GRS into the value of K and the value of RS will decide how much of GM do you have here. In fact, the equation is pretty simple. There is a 2 there. So you can just do it 2 and it will be an equation. Meaning the value of RS and the value of K is going to decide how much of GM do you have for this transistor. Let's say if I go ahead and multiply this current, it's the same W by L if I take. It's nothing but a current mirror, right? And what will be the GM of this transistor? It's exactly same as this transistor, right? So the value of RS and value of K decides what is the GM of this transistor, which is mirrored. Okay, hence this GM that we are trying to mirror is a constant GM. So hence the name constant GM circuit. Now I also mentioned it's called a beta multiplier. Why is it called a beta multiplier? Now this structure overall itself is called as a beta multiplier. Okay, there is beta is also one of the proportionality constant. Whatever C dash you saw, C dash is very much related to beta multiplier. In fact, C dash inverse will be very near to what beta is in an actual circuit. So we are trying to multiply the GMs between these two transistors, or multiply between these two transistors, and or multiplying the GM between GM or beta between these two transistors. So hence it is called a beta multiplier. Meanwhile, if you look at what I out is, I out equations is it's 2 by mu and C ox W by L, 1 by R square, 1 minus 1 by root of K. There is nowhere a voltage is mentioned. There is no voltage mentioned. Hence, it is also a supply independent biasing. This voltage that you use here can be told that this bias voltage is supply independent, and you can use it at multiple places to get the current mirroring. And because it is supply independent, we also call it supply independent biasing. Okay. Now this circuit, how do we really design it? You have the given I load, whatever you say, let's say I finite, right? You have designed for a fixed current I finite. You know how to design the sizing, how to take the sizing. It's pretty easy. You can also take RS, the value of RS, depending on what drop you can have here. And that much of VGS is reduced here. Let's say drop has to be 0.2 volts or 0.3 volts. You already have fixed drop across RS. And accordingly, the value of M1 and M2, the sizing, we can fix it. Okay, this circuit is commonly used as a current bias. Or you may also call it as a voltage bias, because voltage is what we are routing from where the current is generated at the destination. So this is the basic supply independent current. But if you ask me whether is it PVT independent, I already mentioned, no, it is not PVT independent, just a supply independent. But if at all we have to generate a PVT independent current source, what should we do? There could be some question about this. We will see that once we complete the band gap reference, and then we can reach back here. We will be, because constant current, the current IREF is typically, we will have to have a BGR structure for the generation of IREF. Not always, but it is expected to have one. Anyways, we will look at it later about IREF generation. But let's come back to the BGR now. Band gap reference, as the name says. It is a reference circuit, for sure. The name says it is a reference, right? But what is so different about this circuit? Why is it called band gap reference? Every material has, if you look at the device physics, every material has something known as band gap. A parameter or specification, or what do you call, a characteristics of any material. Any material has a band gap. And for silicon, the band gap happens to be 1.2 volt. Okay. And this circuit can also generate a voltage of around 1.2 volt, almost always. That's the reason we call the band gap reference with that name, because band gap reference output voltage is also very near to 1.2 volt. Now, what is the basic concept behind the band gap reference? Do we have some circuit inherently that it can give always 1.2 volt? No, we have to build a circuit. To build a circuit, we have to make use of the characteristics of the device, the materials that are present. To begin with, it was observed that there are some very fixed characteristics of some of the devices, irrespective of where, what process corner it is, everything, irrespective of PVT corners. I mean, irrespective of PVT, let's say, their characteristics are almost always fixed. What is this particular device that I'm talking about? Let's say you have characteristics of a device, some characteristic, let's see what it is later, some characteristic of the device which has a very fixed behavior, something like this. As the temperature increases, the voltage goes on decreasing in a linear fashion. Okay, this is one of the characteristic of something, some device. We'll see what it is. This behavior is called CTAT. Meaning, as the temperature increases, the voltage or the parameter that I'm talking about is decreasing continuously. Okay. And then there is other parameter, other characteristics of one of the device, let's say, which is rising continuously. Assume that it's a straight line. It doesn't look like, although it's a straight line. We call it a PTAT behavior, or proportional to the absolute temperature. So let's say we have a CTAT behavior and a PTAT behavior. And if we add them together, add this and this, you have to ideally get a constant output voltage. CTAT plus PTAT will be constant. Why? Let's say you have a voltage ranging from 1.2 to 0 volts. This voltage is increasing from 0 to 1.2 volt. At the lowest temperature, you add them up, 1.2 plus 0, you get 1.2. At highest temperature, you add them up, 0 to 1.2, 1.2 again. So in every middle point, you go and add them, you will always get 1.2 as output voltage. That is where the addition of PTAT and CTAT voltages give you a constant voltage. Now, there are some catches here. What are the catches? If I have to do a PTAT plus CTAT, to get a constant voltage, the slopes of this CTAT voltage should be equal to the slope of PTAT voltage. If the slopes are not equal, then we are in for a trouble. If slope is different, let's say if slope of CTAT is more than the slope of PTAT plus CTAT, if slope is more for a CTAT, then the output voltage will always be CTAT voltage. Similarly, if PTAT plus CTAT, if slope is more here, then the output will be a PTAT voltage. As long as the slopes are same, are equal, only then you're going to get a constant voltage all the time. Let's come back to the basic concept of somewhere in some device you must have found something that's very much PTAT in nature or very much CTAT in nature. What is that particular thing that we have found out? If you look at the BJTs, bipolar junction transistors, or even diodes for that matter, the diode or BJT's junction voltages. Okay. If you consider a PN junction's junction voltage, that junction voltage, or if you ask me about a BJT, if you diode connected for a fixed current I, it is observed that the VBE, the voltage here is VBE. Okay, for a fixed current, del VBE by del T, or in other words, it's the slope that we are talking about. Okay, this slope is observed to be a constant negative slope, or in other words, it's a CTAT slope. Meaning, you go on observing the VBE over temperatures, the VBE will always have a downward trend, and it is a straight line when you observe from, let's say, 0 degree to 120 degrees. It's always that your VBE is a CTAT curve, and the curve looks like this. Of course, when you look at the VBE by del T, the expression is a bit weird. Let me just put it like this. The IC, the current flowing through the transistor here, is given by IS. It's called something known as a saturation current. For the BJT, it's not the saturation current that we talk in terms of MOSFETs. It's something different, VT. Now VT is given by KT by Q. It's a temperature dependent voltage, Vt equal to kT by Q. Now, IS also has a particular expression, a big one. We substitute everything and it finally, we get del VB by del T. You need not really remember it all the time, but if you know, it's good. If you do not, it's fine. As long as you understand the current profile, it is good. Q by Q. Okay. Now, I mentioned that del VB by del T is a constant number and it is CTAT. Constant number, negative number, which makes VBE as a CTAT voltage. But looking at the expression here, del VB by del T, when it should have been a constant voltage, as a constant number, let's put it as constant number, but we do see that it is also dependent on multiple things. It is dependent on VB itself. It is dependent on VT. It is dependent on temperature. So meaning, although you say that it is a negative number, it doesn't seem to be a constant number as the temperature changes. Meaning the slope that you have here may not be a constant one, but it may have some irregularities, something like this. A very small one, it may not really be observed using, at first sight, you may have to zoom it in and then understand, yes, there is some issue here in the curve. Although for all the calculation purposes, for all the assumption purposes, it can be said that it is a constant negative number and hence VBE is a CTAT voltage. Now let's go back and try to understand. CTAT is fine. You got a CTAT. What about PTAT? Do you have a PTAT at all in the real life? For this, there is another requirement here. Let's say that you have a current I flowing through. It's a constant current I flowing through a transistor of size 1. 1 could be just a reference number. Now, what is VBE here? VBE is a CTAT voltage. Let's say I push the same current I, it's the same, exactly the same current I into another transistor which has n number of transistors, or the sizing is n times. Okay. Now I'll say this is VBE2. What is VBE2? VBE2 is also a CTAT voltage. VBE1 is also a CTAT voltage. Both are CTAT voltages. But there is some difference because of the sizes. In one transistor, the size is 1. The another BJT is size n times bigger than the left side transistor. Hence, there is a difference between VBE1 and VBE2. It's not the same. Now, if you look at del VBE, which is VBE1 minus VBE2, VBE is given by VT ln I naught by IS. This is directly coming from the previous equation. We can solve this equation to get what is VBE. Okay, that's what we have done here. What is VBE2? It is VT ln n I naught by n times IS. There are n transistors and hence n times IS. You get del VBE given by VT ln n. What is VT? VT is KT by Q ln n. Meaning this is a constant for a given number, given n. Q is a constant, K is a constant. What is remaining? It's only T, meaning del VBE is proportional to T. So the difference in the VBE voltage between two transistors, two BJTs, is proportional to the temperature, and hence the difference voltage is a PTAT voltage. So we saw that VBE was CTAT, but del VBE, especially when both currents are same, I is the same, del VBE is a PTAT voltage. So we got both the numbers, CTAT and PTAT. But I also mentioned that the slopes have to be the same. If slopes are not same, then we are in for a bigger problem. Now, how do we ensure that the slopes are the same? Are the slopes same? First thing. There is a fixed number. I'll give you the number. It's around, CTAT is varying at minus 1.5 to minus 2. This is the range, millivolt per degree Celsius. That is the slope of CTAT. The PTAT slope is 0.08 millivolt per degree Celsius. You see, there is a huge difference between the slopes. And in general, for all the calculation, we can take as, you can take either 1.5 or 2. It depends on technology. Most probably, if I remember right, for the technology of GPDK 45 nanometer, the number comes around 1.8 millivolts per degree Celsius. For CTAT, for PTAT, the number is 0.08 millivolt per degree Celsius. What's the difference? Or give me a minute. What's the difference between the CTAT and PTAT? There is a particular ratio that we're talking about, 1.8 millivolts divided by 0.08, approximately 22.5. For in typical calculations, you can look at the textbooks. The numbers given are in the range of 1.5 millivolts per degree Celsius. You can look at Razavi, and it is 0.087 millivolts something, I believe, yeah. 0.087 millivolts per degree Celsius. It does change from technology to technology, but for the calculations, for initial calculations here, we would also, we will go ahead and take the same numbers. However, when we go to actual cadence implementation, we may calculate, you may go ahead with the same numbers first, and then you calculate, you update the numbers, then redo the simulations. I'll give you the entire procedure of how to design a bandgap reference, and we will see what the slope that we get from cadence simulations as well. What is that CTAT slope? What is that PTAT slope? Are we matching the theoretical numbers, or are we off by significant amount? If off, what should we have? What should we be doing to make sure that we get a constant voltage at the output? Okay. So with this is what I remember from my previous batch, that CTAT slope is somewhere around this, and PTAT is somewhere around 0.085 or something. Anyways, the ratio is somewhere around 20 to 22. Okay. So let's go ahead and then look at this. If this 2 is the ratio, the ratio difference is 17.2, meaning CTAT is 17.2 times bigger than the PTAT. the slope of CTAT and PTAT are 17.2 times different. Hence, if I have to get a constant voltage, V out, what I have to do is, let's say I add VBE plus 17.2 times del VBE is what I'm looking at. Okay, that's the slope that I was talking about. What is del VB? Del VBE is nothing but VT ln N. Right. So we can go ahead and say it is VBE plus 17.2 times VT ln N. Okay. Now we understood that del VBE is the PTAT voltage. We have to make sure that we have to add a VBE and del VBE. Where do we add this VBE and del VBE? Is it possible that this del VBE is del VBE is replicated, or it is mirrored, or it is del VBE is manifested in some resistance? It is a very much possible voltage or possible thing to do. Let's say this is the left side one with 1. This is the right side one with N. If the same current flows, I'll just put it this way. I generate a V bias for PMOS where it's the same V bias given. So same current has to start flowing here as well as here. Same current flows. This is VB1 and VB2. VB2 is smaller. I have to make sure that I get del VB somewhere. Now I have to make VB1. Anyways, VB1 equal to VB2 plus some IR drop. Meaning this IR is nothing but del VB, right? It's a difference of VBs. VB1 minus VB2 is del VB, which is IR. Meaning this point, which is VB1, and this point, which is VB1 plus IR, they both have to be equal. How do I make 2 points equal? We have all seen this. How do we make 2 points equal? Use an op-amp. Give 2 inputs to the op-amp. Make sure that it is in negative feedback. How do we make that? That is different. We will see that. Make sure that it is given in the negative feedback and the output is shifted here. Now it's the same current flowing here, same current flows here. We have IR. So this node and this node, they are constant. The nodes VB1 plus VB1 plus IR is constant. Now all we have achieved is del VB only. We have to have 17.2 times del VB. There must be a gain that we are able to get. How do we do that? We have to, what is this? Let me name it as VBGR equal to VB plus 17.2 times del VB. Where do I get this 17.2 times del VB? So I had an IR. How about I do I into R plus some bigger R. Let's say I'll name it as R1 and R2. This is the 1 del VB. I have to somehow add 16.2 times del VB, right? So if IR equal to 1 del VB, I have to have 16.2 times IR to have 16.2 times more del VB, or even any gain, let's say n times IR, if I have, it will be n times del VB, right? So what if I add a resistance here, which is n times R, whatever the gain you want to have, let's say it is maybe 16.2, maybe 17.2, whatever it is, it depends on what is the ratio that we get in your technology, right? And now, what is the voltage here? V out could be n times R plus IR plus del VB. VB. Meaning you have a VB plus you had a very small quantity of del VB. Now it became n plus 1 times of IR, a bigger quantity. Basically, you are able to scale it up. Whatever the voltage you wanted, you are able to scale it up. But did I miss something? There was a particular ln n. That ln n is coming in del VB, right? So it is basically 17.2 VT ln n. So ln n also plays a role there. You can play with ln n numbers, and I confused you with this number n and m. Let's say I'll put it as mr just to make sure that there is already another n that I've used. Okay, so this ln n is also an important parameter. Depending on ln, you can choose n to be a bigger value, 100, 200, 300, any value, so that you get some relaxation with respect to the resistor scaling as well. The overall scaling has to be 17.2. The calculation part and also the next IREF part, I'll be talking tomorrow. I will also be retouching this because I know that it's not a simple concept to understand in one simple class, one single class with less than an hour. Let's have a revision of this particular section tomorrow, and then we can continue to the IREF again. Okay, so you can go look at what we have done today, and then tomorrow I'll be repeating the BGR part again, not the beta multiplier, but the BGR part again, and then we will continue to the IREF part. Okay, so maybe we'll stop here today and we'll continue tomorrow morning.